All right, in this installment, we are going to be talking about noble gas configuration, exceptions to electron configurations, as well as how to construct the electron configuration of ions. So, in order to do noble gas configurations, what we need to do is we have to do the regular electron configuration. So if you look, if I wanted to do the noble gas configuration of carbon, the normal configuration for carbon is 1s2, 2s2, 2p6. And, oops, my bad. The next thing I'll do is find where carbon is on the periodic table. And it's right there. So in order to shorten this and save ourselves mega time, especially for some of the F block elements, what we can do is we can do an abbreviated electron configuration by counting backwards to the last noble gas that we passed. So if I go backwards, 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 that would be helium. So this whole column is the noble gases. What we're allowed to do is we're allowed to start from any of those. I'll just leave that on carbon because we're going to find that. I can start on any of those, and then I can continue with my electron configuration from there. So it's kind of like a shortcut. So what I'm going to do is, because the last electron configuration, or the last noble gas that we did was helium, I'm going to write He. Yes, that's an E. Leave me alone. And then I'm allowed to count from there. So He, that means I have the full configuration of He and everything before it. And I can just pick up starting with 2s2. So that is what I am going to do. So I've got He, and then it's going to be 2s2, 2p2. And that's my abbreviated one. Now, it doesn't do much in the way of carbon, mostly because it's so small to begin with, so it doesn't really bias anything. But for some of the bigger elements, like iron here, we can save ourselves a decent amount of time. So looking at where iron is and counting backwards, you got to make sure that you count all in a line. So if I count backwards here, 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 there's K, and then go the next line up, that's Ar. So that means I get to buy myself a little space by starting with argon. So I'm going to go Ar. And now I can start right after argon, which is going to be 4s2, and then 3d, 1, 2, 3, 4, 5, 3d6. There you go. So that's it for iron. Now, you can do this for anything, for any element. You just have to make sure that you count backwards. It can be a little bit tricky to count backwards for some of the things in F blocks just because they plug in right here. But count backwards, backwards, until you get to the last noble gas, and then you're good. So the other thing that you need to know about electron configurations is that there's no cheating. So see that? That's argon, and argon lives right there. Argon is a noble gas. So the one thing you can't do with noble gas configuration is just go, ha ha, I'm so smart, look at that. It is its own gas configuration. The whole point of noble gas configuration, and really any electron configuration, is that you're showing where the outer electrons exist in space. And so you need to go back one. So if I look up here with my little pointer, you can see that back one would be neon. So you're allowed to start with neon, and then you can go on to argon. So argon would actually be neon, and then I'm going to go on to 3s2, and then 3p6. So you have to give some sort of information about the electrons. You can't just kind of mail it in. All right. Now that we've covered that, I want to go over exceptions to the rule. So the next element I want to do is chromium. And then we're going to do copper, which lives right there. And then we're going to do silver, which lives just below copper. So all of these are exceptions to the electron configuration rules, because what they can do is they can move their electrons around to become a more stable version of matter. So let's do the normal electron configuration of chromium. That is going to be argon, Ar, and then 4s2, 3d, 4. So you need to understand that there's some sort of hierarchy here with the filling of orbitals. There's happy, there's sad, and there's kind of like, you know, I don't really care, dude. All right? So, electron configurations are the most stable when their orbitals are completely filled. Completely filled. So, yay, we're completely filled. That is the most stable arrangement of matter in three-dimensional space. All of the electrons have the maximum repulsion. Everybody's happy. Second best to that is half-filled, because at least they're getting away from each other. It's not the best because the repulsions aren't quite maximized yet, but it's not too shabby either. And then the sad face is just anything else. So in the case, if we look back at chromium, oh wow, hello, oh dear mother of God, hang on. Everybody just time out. Never mind, I can't do that anymore. All right, if we take a look at chromium again, it's Ar 4s2 3d4. So this d4 right here, at the moment, isn't anything else. A d suborbital is half filled at 5 and completely filled at 10. Now I can tell you right now we're not getting to 10. It's not a possibility. Not going to happen. But what we can do is we can take one electron from the 4s2 orbital and we can loan it over to here. And what that means is now I have Ar 4s1, which isn't bad. It's not the greatest, but it's not terrible. And then I have 3d5. So what that does from an atomic perspective is it makes the atom as a whole more stable. So it also changes the number of valence electrons. So if you notice, the regular configuration of chromium, the highest energy level between 4 and 3 is going to be 4. And we have 2 valence electrons right there. With the movement of one electron from 4s to 3d, now we only have 1 valence electron, which is fine. It's going to change the charge of the ion a little bit. Not a big deal. So now let's go to, why is this all grouped? Okay, I quit. Now let's go to, I shall make a new one. Now let's go to, where was I? Copper. Copper's right there. All right, so move all that down a little bit so it fits. And I'll use a different color just to differentiate. So copper's regular electron configuration starts at argon, Ar, and then it goes to 4s2, 3d9. So again, taking a look at that that final electron, that orbital right there, not exactly the most stable thing in the world. It's 3d9, it's 1 away from being completely filled, so right now it's down with everything else, but it could be super, super happy. And so again, what's going to happen is an electron leaves the 4s and is going to be moved to 3d9 to make this more stable. So it's going to become Ar 4s1 3d10. Now more stable. Silver is the last one that you need to be familiar with. Silver is, let's see, silver is right below. So it's basically an identical electron configuration of copper, except we're going to move down a noble gas, so we're going to start a krypton instead. So this one is going to be Kr. And then we're going to go to 5s2, 4d9, and you can see the same thing happens. So instead this is going to be Kr, 5s1, 4d10. Now don't get all antsy in the pantsy about this. The only time that this is going to happen is if you're here, copper, silver, or if you are chromium. All right? Don't be begging, borrowing, and stealing electrons from other things just to kind of like satisfy this whole stability thing. For the most part, that usually only happens in the d suborbital. These are the only exceptions that you're going to be responsible for. So, but if you do see something like copper, make sure that you don't leave your electron configuration this way. Take the 3d9, borrow one from the s, and then make it 3d10. All right. So now let's talk about ions. So as a review, we have two types of ions. They can either be cations, which are going to be positive, anions, which are going to be negative. Cations are the metals in the periodic table. So we've actually got that little staircase there. And then all of those are metals. All of those are going to make cations. So they need to be losing electrons to make their overall charge positive. Anions are going to be, hydrogen can be both. So here, let me actually color that in both. And then the non-metals, which are all right there, those are going to be anions. In general, noble gases don't have a charge. We're not going to make ions out of those, so don't do it. So what we need to do is we have to predict where these electrons are going to be gained or lost from. So I'm going to do the same thing where I do the abbreviated electron configuration, and then we can figure out what happens with the outer electrons. Those are going to be the ones that are most likely to be lost or gained. So on the periodic table, the most stable elements that are on here are noble gases. So they have a completely filled s orbital and a completely filled p suborbital. And so as a consequence, they have 8 electrons in their valence shell, which means they satisfy the octet rule, if you remember that from bio. So let's find magnesium. Magnesium is right there. It's an alkaline earth metal. The electron configuration for magnesium is going to be, I'll write it above, it's going to be, if I cut back to neon, 3s2. All right. Now, this electron configuration, we need to lose a total of 2 electrons. So see that right there? We have to lose 2 electrons. And when you write it out this way, it's kind of easy to see where those 2 are lost from. So the ones that are going to be lost here are going to be this. This whole orbital disappears, and now your ion, Mg2+, is what's called isoelectronic. That means it has the same electron configuration as neon. So Mg2+ now becomes He, and then it's going to be 2s2, 2p6, just the same as neon. There you go. Now, how can you tell the difference? Well, the number of protons will still be different, because for it to remain magnesium, it's still going to have the same number of protons. It's still going to have 12. Neon has 10. And so the electrons are carried in a little bit different way, but the total numbers and the regions of space that they occupy are going to be identical. So next one we've got, I chose a cation and then an anion, and then something maybe a little bit more tricky. So we've got N3-. So if I try to find my N3-, N is right here. It's element number 7. And I need 3-, which means it's going to gain 3 electrons. okay, to be isoelectronic to a noble gas. So let's just do our regular noble gas configuration for nitrogen, just regular old nitrogen, the atom, He, 2s2, 2p3. So right now it's not too bad. The p suborbital is about half filled, but what we can do is we can add 3 electrons here, and it could be completely filled. So our ion, our nitride ion, is going to gain 3 electrons, He, 2s2, 2p, and now it's going to be 6. So you can see what it does to the electron configuration. It makes it a ton more stable, right? The last one I'm going to do is indium 3+. So it's a little tricky because it's right here. And we have to decide which 3 electrons it's going to lose. So this is element number 49. So again, I'm going to do my abbreviated electron configuration of just regular old indium, the atom, first. That's going to be Kr. And then it's going to be 1, 2, 3, 4, 5 S2, 4 D10, and then it's going to be back to 5 P1. All right. The reason why I chose this one is because the electrons need to be lost from the outside of the atom first, which means they need to be lost from the highest energy level first. So what I've got here is I've got a 5s2 hanging out. 4 is a little bit inner, and then I've got 5p1. So in order to make a +3 ion, I'm not just going to take this 1 and then 2 more here, leaving a d8. That'd be really unstable. Instead, what happens is 5p1 will be lost because that's unstable to begin with. The next best thing is to leave the d10 alone and take away the 5s2. And so our new electron configuration of the indium 3+ ion is going to be this, Kr. But I still have that extra 4d10, which sets it apart a little bit. So now hopefully you can kind of see where we pull from in order to get ions. Always take from the highest energy level first. Never try to just take them in order. That doesn't go very well. So what I did was I set up kind of like some challenge problems here. So I did manganese, which is a D block element, and it is right there. Manganese is element 25, and it has multiple oxidation states, which means it can have multiple charges. You see over here, this is Mn2+, Mn5+, Mn7+. And so what I want you to do is I want you to pause the video here, and I want you to come up with the electron configuration of all 3 of these. All right, let's look at some answers here. So here's manganese. I'm going to put the little pointer on it and then hope it doesn't move with all my nonsense. The first thing I'm going to do is I'm going to write just regular old manganese out. So that is going to be, and I'll leave this at the top so that we can refer back to it. It's going to be argon, and then it's going to be 4s2, 3d, 1, 2, 3, 4, 5. All right, so we've got a couple options here when it comes to removing electrons. We have a D5, which is half filled. It's not bad. It's not perfect. We have a 4s2, which is certainly completely filled, so it's better than half. This isn't the worst thing in the world, but we do have to be strategic about what we take off here. So I've got a +2 ion that I need to make. So either I can change this to D3, which would be completely yucky and gross, or I can just get rid of this altogether, which is a much better option. And so I'm going to go there. So I'm going to say that this one is AR. Now my 4s2 is gone, but I still have remaining a 3d5. And that makes it a +2 ion. Now looking at Mn+5, same situation as above. I've got a 2 I can get rid of, or a 5 I can get rid of. I could get rid of this 2 and then another 3 over here, but that leaves D in a really terrible spot. So what I'm going to do is I'm just going to get rid of this entire D suborbital and move on with my life. So I've got AR 4s2, which is fine, right? Because that's still completely stable. Not a big deal that it's not completely isoelectronic to a noble gas. Now I've got Mn plus 7. So coincidentally enough, if I look up here, right, I've got a 5 and a 2, 6, 7. I can get rid of both of these orbitals, in one case orbital, one case suborbital, and then that's where I can get my plus 7 to come from, which means it's just going to be isoelectronic to AR. So because it's isoelectronic to AR, everything else left, I'm going to rewrite this. Remember, we can't just leave it AR. It has to be NE. So let's go back one more. And then let's just fill it out. So it'll be 3s2, 3p6. So that is how you make ions. All right. This concludes this portion of Electron Configurations Advanced. If you want to learn a little bit more, you can check out some of the other videos. I did one on orbital theory and electron configurations as a beginner, including D and F block. And I'm also going to do one on off-bow diagrams, so you can look for that one as well. All right. Thank you. Bye.